Okay, so we are looking at part D now, and so we are given some experimental data, and so that is very important with what we're doing. So let me draw out our tanks. And so we have our flow rate in, our first tank, we have our height of H1, and we're going to do our flow rate in being Q1. Wait, no, when I coded it, I used QC. Okay, and so from that, we have our flow rate out. Oh, and don't put an arrow there, Andrea, because it's going to go into another tank as always, but that's Q2. And that is going to have a height of 2, and the flow rate out is yep. Okay. So we have our flow rate out. And so when we're doing this, we are wanting to control our H2. So that means we're going to have an H2 set point. And so that is going to be basically within that area. And so for this, we're going to have to use some transfer functions. So we have a flow rate in, it's our QC, and then we have our GP1, which is inside of that tank. And then we have our Q2, and then we have our GP2, which is our flow rate, which all of our flow stuff and transfer functions within that one. And we have a flow rate coming out, and we're going to call this a capital H2. Okay? And so with this, we are going to go and code this in Python. All right, so now we are going to look at our system and say, hey, let's set our measurement device equal to 1 and see how the system feedback works. System feedback controller works. So we're going to start with making some data points. So again, this is all a theoretical case. So we're going to start with making a range of values, and so this is going to be our random function. So RNG, just to make our lives easier. We can't really write range. I want to write range, but it adds for confusion because there's a range function in Python. So that's going to be np.random.random state, and then boom, boom, boom. So we're going to do 1, 2, 3. All right, shift enter. Cool. And so then we're going to start out making our experimental data points. So we're going to do T experimental, and this is going to be our setting up our NP linspace. Let's do from 0 to 15 seconds, 50 iterations. And then we are going to make our transfer function for our process. So I'm just going to go TFP. And we're going to pull in our TF mult. And that is, let me just go up here. Where's my TF mult? Where's a good TF mult to use? Okay. And we need these guys right here. Beautiful. Wonderful. Okay. Then we are going to start setting up our T2 as not T2, our transfer function of the process as a stepwise. And so this is going to be underscore comma H2EXP. And that is going to be our TF underscore P dot why am I forgetting what it is? Step. Just doing a stepwise. Oh, goodness. It's been a long day. And our T is going to be equal to T experimental. All right. And then our H2 experimental, we're going to have that equal to our normalized range. And so to do this, our location is going to be equal to our H2 EXP. And then we have to scale this. And so we are given a distribution, our standard deviation. And so that is our scale, and we were given 0.02. All right, and so now it's time to graph our points. And so since this is experimental data, what we are going to do is we're going to have the mode be marks. Instead of a line, we're going to have just the plot the points. So our X is going to be our T experimental. Our Y is going to be our H2 experimental. And then I don't need the name, but I do need mode. And that is going to be markers. Shift enter. Beautiful, nice curve. Wonderful. So if we were to look at the first order exponential graph of this. So let's draw our quick graph. So if you think of just first order exponential, you think something like this, and that's assuming it's starting at the origin. And so if it were to be starting at the origin, so I'm going to write it down here, origin, that, well, x equals 0, y equals 0. And so with that, instead, we would have our k1 minus exp of time over tau. Okay, and so that is if it's starting at the origin. Well, in our case, that is not true. So if it is not starting at the origin, this is what it's going to look like for us. So it's starting at a different x value. And so we have this little gap right here, and that's going to be called theta. And so theta is our dead time. So we have to take that into consideration with all of this. And so basically all that changes is that we have k 1 minus exp negative time minus theta over tau. All right, and so that is what we're looking at for our graphing. Now we are going to start doing our function, which we just did the equation for earlier, but however, we have to import one more thing. So let me, hopefully it doesn't glitch out if I try to do it right here. Import, actually, no. I'm gonna go all the way back up here. So we are gonna add in a function right here, which is minimize. And so we are going to use that coming up because we not only want to optimize, we also want to minimize. And so now we are going to make a function. So defining our FOPTD. Okay, V. Beautiful. Okay. And so that's a vector. And so our K, which is our controller gain, we have tau, and then we have theta, which is our dead time. And that is going to be equal to our vector that there we go. Okay. All right, so here's where we put in our equation that we just talked about on the whiteboard, which is our k times 1 minus jnp exponential negative t pardon me, that was very rude. exp over our tau. All right, and then we are going to return jnp dot where of our t exp when nothing theta all right, so we have shift enter. Cool. All right, and so now we are also going to define our guess values for v. So what we're going to do is put in our v underscore g for our guess, and let's put in 2, 4, and 1. All right, and now we're going to define another function, which is SSE, and that's going to be a v, and we are going to return jnp dot sum of our H2 experimental minus our FOPTD of V, and we need to square this. So let's add in we're going to add in another guy right there so that we can square, wait, no. Yes, no. No. Whoops, I already added in, no, stop. I already added one for that. All right, shift enter. Okay, that should be okay. And then our result is going to be this, where we're going to use our minimize. And we're going to do SEE, SSE, comma, V underscore G. Shift enter. Cool. So now we are, oh, sorry, my hair got in the way. All right, so now we are going to be graphing both our data points and this line. And so what we're going to do is we're going to take this from up here, put this guy down there, copy this guy, put that right underneath. Now we're going to have to change the second one to be line. And instead of that, we have our y is equal to res dot x. Oh wait, no, sorry. I need my FOPTD of that. I do have to say lines. Yep, cool. There's that. So now we are going to determine our KC and our reset time for the PI controller. And so we're going to start with our K, our tau, and our theta, and that is going to be equal to our res.x. Whoop, you didn't want to enter? Please stop. No, I don't want to see that. Stop. There we go. Okay. And then we're going to put in our KC is equal to our A value, which is we're given is 0.586, multiplied by our theta divided by tau to the power of our B value, which is negative 0.916, and then all that divided by K, and that is our KC. Shift enter. No. Oh, I put Farah. There we go. And I forgot to put in KC. What do I want? Okay, nice. Beautiful. Okay, and then now we are going to do our tau I. So our tau I is equal to tau divided by 1 point, oh, why did I do a space? 1.03 minus 1.65 times parentheses theta divided by tau. Boom. Okay, and then we want, well, let me just double check. Shift enter. No, that is wrong, my dude. Oh, because I did 1.65. 0.165. There you go. No, wait. Yeah. Yeah, that's fine. Tau D is going to be equal to 0. All right, so what we're going to do now is basically because I like doing it in separate sections, so I keep all of this in case I have to go back and refilm something because it didn't go well. I am going to go all the way back up to our graphing section. Where are we? Okay, so I need to put back in our TF mult with TF forward. I'm gonna take out the P and ID part, but boom, 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 and we're gonna take out boom. I don't need that one. Okay, so we have that, and then I also need to snag this guy. Shift enter. And then we're going to also snag our coding for the graphing of the Bode diagram. All right, so now I'm going to have to adjust it a little bit. So I'm going to come in right here, and I am going to do W is equal to NP. Oh, not capital. My caps lock is on. No. NP dot log space -2 to 100. Okay. Shift enter, shift enter. I was wondering why it looked weird. We need to add in our ratio. Our ratio is equal to 10 to the power of dB over 20. That still doesn't look right. That should not be there. What is wrong? Oh, I'm dumb. I needed to keep the PID. Oh, I was so confident, too. Give me this guy, please. Give me that guy again. Put you back in. Shift enter, shift enter. Why am I still having issues? Oh, because this time I capitalized Casey. Is that what it was? There we go. Beautiful. Okay. Such a minor thing. Okay. So let's do our analysis of it. So if we're looking at 180, we see that as far as we're concerned, it never crosses 180. And so that's really good. That means that it will not become unstable in that sense. And then let's do our other one, which is where it intersects with 0. Let's see, round 0.61. And that's about at 120. So 120 to 180, that is about 60 degrees. And so that's a pretty big phase margin. So that's pretty good. That means it'll take a while for it to become unstable. So that is our Bode diagram for the PI.